Okay, welcome to lecture 7. So today we are talking about quantifiers. These are things we've secretly been using without saying what they were, just because they show up so often, they're unavoidable. And now we want to break it down, try to understand them. So let's think of one specific example. We often see statements like this. For any x or something where x could be some type of number. So let me just say, like, for any non-zero, for this specific example. So for any non-zero x, and then you say something that x might do. So like this, x squared is positive. So we've seen statements like this. And now we just want to sort of break it down and try to understand it better. Okay, so the phrase x squared is positive, that, remember, is not a statement on its own, because whether it's true or false depends on what x is. So it's not always positive. What kinds of things you plug in. So it's not exactly a statement, but it's still important. And we want to think about what exactly it is. So, but it is something which is true or false depending on x. So we do have a name for such a thing. So such a thing is called an open sentence. You might also hear the phrase predicate. But name doesn't matter so much. The point is, it's something which does take values, truth values, true and false. So it's either true or false, but it changes depending on the values of x that you plug in. So then what we can do is we label it as, because it depends on x, we don't label it just as p like we have been doing. We actually label it as p of x. So it's sort of like a function because it changes depending on x. So we call it p of x, not just p. So before we were being a little bit sloppy and we were calling things like this p or q sometimes. But really, we should have been calling them p of x the whole time. But that's okay. That was before we knew better notation. So here's another example of a predicate or an open sentence dependent on x, something like that. Something like this: x plus 3 equals 10. Or x is bigger than 5. Lots of things are open sentences. These are much more interesting than statements. And in fact, these are the things we've been studying for a while now without calling them anything. And that's because they are more interesting than statements in math. Statements that you put inside of, like, if-thens and things are very boring, because then you can only say stuff like 3 equals 3. Okay, that's a true statement. 3 equals 7. Okay, that's a false statement. Very boring. You can't really do much if you combine statements like these into if-thens. Doesn't really do much. But when you put open sentences into if-thens, that's when you get more interesting conditional statements. And those are exactly what we have been studying. Okay, so then when you have a predicate, you can create a statement by quantifying it. So that means writing something like this. So for any even number n, n plus 2 is even. So this entire thing is a statement, but just this end piece here, that's a predicate that you could call P of n because it depends on n. So you could write this as, for any even number n, P of n, where P of n means n plus 2 is even. So this is the nice part about open sentences, is you can label them like this. And we can also have open sentences or predicates with more variables. So let's do that too. So what I mean is something like this. You could say, oops, you could say, how about this? For any pair of numbers, A and B, and then you say predicate. So like A plus B is 10. So this is very similar to the previous statement, except there's two variables. So this predicate here, you wouldn't just call it P of A or P of B, you would call it P of A comma B, because it depends on both. So A plus B equaling 10 could be true, could be false, depends on A and B. So that's why it's a predicate dependent on two variables instead of just one. And these are, there's no reason that you have to stop at 2. You could have many more. So you could have predicates with more. So it doesn't have to stop at 1 or 2 or 3. As many variables as you can think of, you can have in your predicate. Okay. So then, again, these are not statements, they're predicates, but they form a big part of statements. They help you build statements. So how does that work? How do they form statements? Well, they form statements when you quantify them. So that's why this section is called quantifiers. So you quantify the variables. You declare something about the variables. So up here, we're saying that A and B can be any numbers, and then we've created a statement. Up here, we've said n can be any even number, and we've created a statement. So that's the kinds of things you can do. You can also quantify a little bit differently. But that's what's going on. So you form statements when you quantify the variables. Let me actually add on to this by claiming that the predicate, I'll just pretend it has one variable for this explanation, by claiming that this is true for some specified choices of X. Okay, so let me write down the definition of what I'm talking about, and then we'll go through more examples. These already are examples of what I'm about to define. So the phrase for any, or you could also call it for all, or for every, basically anything that sounds like this. These are all the same thing. It's called the universal quantifier. So why is it called the universal qualifier? It's because when you use it in a statement, for any x of some kind, a predicate happens, what you're doing is you're claiming that the predicate is universally true. It's one way to think about it, for any of the x's that you described, not just for one or two, but for all of them. So over here, you could describe what kind of x's. You could say, for any x even number, I'm writing it sort of backwards, or you could say odd number, you could say prime number, whatever you want, all sorts of things. And so it's called, so this is called the universal quantifier because you're saying that the predicate is true always for the values of x that come after the universal quantifier. So whatever you decide to say there, even numbers, odd numbers, whatever you want. And we even have a special notation because we use this phrase so much. We write this upside down A to mean the same thing. It means for all, or for any, or whatever the appropriate phrase is. That means the same thing. So then, here's an example we can think about. If I write this, if I say for any non-zero number x, so I'm using the universal quantifier for any, and then I'm describing the types of numbers that x is allowed to be, and then I'm going to write a predicate. How about this? X squared is bigger than 0. So this is something I can write now with my fancy new notation. And so what is this claiming, or what is this statement saying? Claim is that this guy is always true for non-zero numbers. And if that is true, that x squared is bigger than 0 for any non-zero numbers x, then that would mean that the whole statement is true. So in this case, it is true. But we won't go through it too much until we get to more examples. Okay, so the key phrase is always, or that's exactly what for all means. Okay, so that's the universal quantifier. So this other one is called the existential quantifier. And it actually sort of comes in two pieces, but we're going to call this piece the existential quantifier. So there exists, or you could say there are, or there is, or something like that. Any phrase that's like this is the existential quantifier. How do you spell existential? Nobody knows. That's probably right. Why is it called the existential quantifier? Well, it's because now you're claiming that you're claiming the existence of something satisfying the predicate that comes afterwards. And again, this one has fancy notation. So it's written as a backwards capital E. And the phrase such that is usually written after this, the description of what the variable can be. So here's another one. So here's an example of using this. So you could say a statement like this: there exists, and then you have to say the type of thing that's existing. So you might say like an odd number x, and then before the predicate, you always write this phrase such that. It's not really part of the predicate. It sort of comes in a pair with there exists. These sort of come in a pair. You have to say them both. So there exists an odd number x such that, and then you say the predicate, you say the statement that is sometimes, not really a statement, sorry, the thing that is sometimes true, sometimes false, depending on x. So I could say something like this, x plus 10 equals 0. So this is another example of a predicate. Could be true, could be false, depends on x. This is the existential quantifier. And it's called that because it's helping us claim that something satisfying P of x exists. Okay, it helps us claim something making P of x be true exists, but in the specified possible values of x. So the specified possible values of x this time are odd numbers. So you would never just say there exists an x such that x plus 10 equals 0. If you said that, people would assume you're talking about some specific types of numbers or something. But instead, we want to be a little bit more careful and precise. You would say there exists, and then you would say what kinds of things you're looking into where this thing could exist. And then you're saying the property that it satisfies, the predicate. Okay. So let me look at my notes for a second. So, okay. Okay, so now let's think about the truth values. So when are statements like these true and when are they false? So again, the predicates themselves, that's not a statement on its own. The universal, or the quantifiers are not statements on their own, but together they create a statement. So we want to assess the truth value of the entire statement as one big thing, which means we're not zooming in too much on equations. We're not just looking like, okay, that's an equation, I'll solve that or something. No, we're thinking about it all in one big context. So when are statements like these true? Now here's the answer. So a for all statement, if you claim that for all some things, something happens, well, it's only going to be true if exactly what you say, if it always works. So it's only true when P of x is true for all, hence the word for all values that x can be. But a there exists statement, meaning a statement that is quantified by there exists, that's true when P of x is true for at least one value that x can be. Because you're just saying that something exists, you're just saying that it happens at least once somehow. You don't care how many times it happens, as long as it happens once, it's true. Okay, so let's assess a bunch of little quick mini examples. So if I say for any x, so I'm going to start saying it like this to hint at something later. For any x in the real numbers, so I'm going to say it like that instead of saying for any real number x. just because later on it's going to come in handy. So for any x in the real numbers, so real numbers, that just means any number you could possibly think of. We're not going to define it till later, but it's any number that's not an imaginary number is a real number. So the statement is for any real number x, x squared is bigger than 0. Let's see, is this true or false? You might think it's true because, yeah, when you square something, it becomes positive, but you're forgetting about what happens when x equals 0. So if x equals 0, then what you get is 0 is bigger than 0, which is false. So because it's true for a bunch of values of x, but not all of them, it's false. Okay, so x squared bigger than 0 is true for lots of values of x, but the point is it's not for all. It's got to be all, not just most. Okay, what about this one? For any x in the integers, so let me remind you what those are. Those are numbers that look like positive or negative whole numbers. So it could be like -1, -2, 0, 1, 2, and so on, like that in both directions. So for any x in the integers, the integral of x to the n, remember this rule? What do? You add 1 to the power and you divide by it, plus c. So is this true or false? Oh, you love this rule. You must think it's true. Wrong again. Sorry, false. Why is it false? This rule does work for most x's in the integers, but not all. So this guy does not hold. Do you remember which one it doesn't work for? If you remember your calculus, if you've tutored calculus lately, does not hold for n equals -1. So remember that the integral of 1 over x, that's what happens when you do -1 power, is actually ln of x. Whoops. The rule works all the other times, but not there. So this one's also false. Okay, so yeah, I am just going to give you a bunch of false statements to help you think. Okay, let's switch over to there exists. So there exists an x in the real numbers such that, and then I'll say my predicate, such that, what do I want to do? X squared plus 1 equals 0. So now all I'm looking for is one real number that solves this equation. Well, too bad, it's false. You actually need imaginary numbers. So no real numbers work. You actually need to use imaginary numbers. So you'd have to use I to make this work. So if I changed it to there exists an x in the imaginary numbers, then it would be true. So when you're talking about these quantifiers, you really have to look at what kinds of things you're allowed to use. So are you using real numbers? Are you using integers? Later we'll learn much more fancy things that don't involve numbers at all, but the point is you have to look at what your variable is being quantified over, is one way to say it. What are the types of things your variable could be? Okay, so here's another one. There exists an x in the integers such that 2x plus 3 equals 4. This guy is also false. Yes, 2x plus 3 does have a solution when you set it equal to 4, but it's not an integer, because if you try to solve it, let's see, can I do this? I get a half is the solution, but it's not an integer. So the statement is false because you're claiming that it there exists something in the integers that makes the equation hold. Okay, what about, let's see, there's a bunch of false stuff. Okay, I'll switch it over. Here's something true. For any function of the form x to the n, the derivative of that function, well, I guess people just write f prime, huh? Let me do that instead. The derivative will be, you bring it down, and yeah, subtract 1. This guy's true. Yes, this derivative property does always hold, no matter what x to the n is, if it's x squared, if it's x cubed. I'm being a little bit sloppy here. I really should say for any n in the real numbers, instead of trying to say for any function. I was just trying to be a little fancy. Let me change that. Let's do it like that. For any n in the real numbers, yes, the derivative of x to the n is this. Now I got to change this. See, this is why I didn't want to do it this way. Okay, I can do it though. Derivative, I'll just say it like this, of x to the n is, bring it down, subtract by 1. Yes, this always works no matter what n is. So this is true. And then I guess I got to give you a true existence one. So there exists an x in the even numbers. Let me do this. So instead of writing such that, mathematicians are lazy. So we just write st. This means such that. I forgot to do that earlier. I could have saved so much time. Such that. This is a true mathematician greatest trick. So there exists an x in the even numbers such that x plus 2 equals 0. This is true because -2 is an even number. And so there exists something in the even numbers that solves this equation. Okay, so that is it for today's lecture. I will see you next time.